It's a weather term gaining momentum in recent years.
The latest atmospheric river will continue to batter California today.
It has been a wet winter season so far. It's an El Nino season. We have big low pressure systems here, but also a thing called an atmospheric river.
The state is so saturated from at least 11 atmospheric rivers so far this season.
They can transform landscapes, overwhelm infrastructure, and reshape our understanding of extreme weather.
It's more than 1,000 miles long, several hundred miles wide, and it's a big deal for states like California.
Atmospheric rivers can actually produce very heavy snow, flooding, even mudslides.
Today, we're going off the radar and into the sky to uncover the history and mystery of atmospheric rivers.
But it wasn't until 2003 that I noticed the AR paper, the light bulb went off. I'm like, oh, that's exactly what we're studying.
I'll be talking to Dr. Marty Ralph, the man that put this weather phenomenon on the map.
It became obvious at that point to me that this was a super important phenomenon.
We'll hear about the scale he created to rank them.
In the face of an absence of something, we've invented something that's shown value.
And why further research to understand ARs is so important.
60% of all bomb cyclones have an antecedent AR present.
I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the oceans, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do.
Audible's Best of 2024 picks are here. Discover the year's top audiobooks, podcasts, and originals in all your favorite genres. From memoirs and sci-fi to mysteries and thrillers, Audible's curated list in every category is the best way to hear 2024's best in audio entertainment. Like a stunning new full-cast production of George Orwell's 1984. Heartfelt memoirs like Supreme Court Justice Ketanji Brown Jackson's Lovely One. The year's best fiction, like The Women by Kristen Hanna, and Percival Everett's brilliantly subversive James. Audible. There's more to imagine when you listen. Go to audible.com/imagine and discover all the year's best waiting for you.
Hi, everyone. Happy December. Thanks so much to all of my new listeners for following along. December is often a time of no new content in the podcast world, but that is not the case with Off the Radar. I have some amazing episodes of the podcast coming out this month. In fact, next week I'll be doing a wrap-up of the 2024 hurricane season with the Deputy Director of the National Hurricane Center, Jamie Rome. Something else I'm covering, we're going to take a look back at the 2004 Indian Ocean tsunami. It's hard to believe it's been 20 years since that devastating event, but tsunami research has come a long way in 2 decades, and I'll be sharing that along with a heartbreaking story of survival. We're also working on an end-of-the-year episode in partnership with the National Weather Desk. We're going to take a look back at the biggest weather events of 2024. So make sure you hit that follow button wherever you listen to podcasts so you'll be alerted of all of these new episodes in December. Today on the show, we're covering all things atmospheric rivers. If you're not a meteorologist or you don't live in an area affected by these, you may not be familiar with the term. But even if you are familiar, there's a lot to learn from today's guest. Dr. Marty Ralph is the scientist that really put these things in the public eye. He created a research center to study them. He created a scale to rank them. And he got researchers from all over the world to help in this effort, like rallying the hurricane hunters to fly into them during their off-season. I learned a ton about ARs today, and I hope you do too. Here's my interview with Dr. Marty Ralph, Director of the Center for Western Weather and Water Extremes at the Scripps Institution of Oceanography. Dr. Marty Ralph, thank you so much for talking to me today about something that I think a lot of people still need to learn a lot about, even meteorologists, because I'm a meteorologist. I did not learn about atmospheric rivers in college. Or if I did, I was sleeping through that portion of the class because I also went to college on the East Coast, and most of my career has been on the East Coast, and this is very much a West Coast problem. So let's dig into atmospheric rivers today. And I want to talk about you and your position because you have this very big role as well. Can you tell me what your job is?
Yeah, I was in NOAA for about 20 years as a scientist and program manager, and then I left to go to the University of California, San Diego, Scripps Institution of Oceanography, to start a center that was really focused on atmospheric rivers and in particular Western U.S. weather and water extremes. It's called the Center for Western Weather and Water Extremes. CW3E is our nerdy nickname. And I'm a meteorologist, and over the last 11 years have been working intensively on the AR topic and its application to water management.
And what is your team like? How many people work there?
I have about 100 people now, and we are very diverse in many ways, including in terms of discipline, like hydrology, meteorology, oceanography, climate, water resource engineering, supercomputing, field engineering, etc.
Okay, let's start with the most basic here of questions, which is, can you summarize for me and give me kind of a basic definition of what an atmospheric river is?
It's remarkably what the word suggests. It's literally a river in the sky, but it's a river of water vapor pushed along by the wind, unlike a terrestrial river, which is liquid, moved by gravity. And it's much larger than a terrestrial river in terms of its spatial extent because, water vapor is much less dense than liquid. So an average AR is about 500 miles across and 1,000 miles long. And if you slice across it like you would maybe a terrestrial river and calculate how much water is flowing down the AR, I use AR short for atmospheric river, how much water vapor is flowing down the AR. An average AR is 25 Mississippi rivers worth of water, but it's vapor instead of liquid.
We often hear about these on the West Coast. Do they only occur and impact the West Coast of the United States? Where do they typically occur?
We have learned the most about them on the U.S. West Coast, but they're a phenomena that spans the globe for the most part. Unless it's a super dry area, then there's just not enough water vapor to be qualified as an AR. The west coast of mid-latitude continents like Western U.S., Western Canada, west coast of Europe, west coast of South America, down to Australia, New Zealand, even west coast, even the southern tip of Africa. They're very important to water supply, especially in Mediterranean climates. They also produce the majority of flooding in those climates. However, they also hit other parts of the world, such as the Gulf Coast and the East Coast. Nor'easters, which our East Coast colleagues and community are very familiar with as important weather makers, they often have, the big ones have a major AR embedded in them. And the details of that feature actually really influence the details of the local weather that occurs with the nor'easter. It's also true that the polar regions have ARs. They don't carry as much water vapor, so we've actually just developed a new scale, extension of our existing scale for ARs that applies to mid-latitudes. We've now extended it for polar regions, and it just got published yesterday.
Wow. Okay, I want to go back to that in a little bit when we start talking about scales. But the term atmospheric river, has that been around for a long time, or is it just gaining momentum now?
It emerged in the early 90s in a series of 4 or 5 papers that were published in formal journals. And the one that I saw was a 1998 paper that I first saw, which I noticed in 2003, this paper that had been published in 1998. And it had been pretty much the last paper on ARs until I got involved. And in the few papers that were published prior, the concept of ARs was defined and its importance was illustrated. But it just didn't catch on. And in the same year as that paper was published in 1998, just serendipitously, I had led a field campaign with research aircraft off the West Coast to study storms that were creating a lot of rain and snow on the West Coast. Happened to be a big El Nino year, so it got a lot of resources and attention. And then that year was also a year when a new satellite type of data became more readily available, called microwave imagery that showed the atmospheric water vapor, integrated water vapor, we call it. And those images, there were enough polar orbiting satellites to stitch them together into a coherent single image at a single time over a big swath of the Pacific. And these long, narrow ribbons of large water vapor content stood out like a sore thumb. And it turned out in that experiment called CalJet in 1998, we had flown across those things. So we measured them carefully, and they were atmospheric river conditions. But it wasn't until 2003 that I noticed the AR paper that the light bulb went off. I'm like, oh, that's exactly what we're studying. And it became obvious at that point to me that this was a super important phenomenon, and that we could then formulate studies and data collection and modeling to better understand them. It was super obvious from the very beginning that they were the real rainmakers on the West Coast. Now we know that on the West Coast, 90+% of flood damages are from AR storms. 30 to 50% of water supply of precipitation in California is from AR storms. And they really stand out compared to run-of-the-mill storms.
So, Marty, you are the reason then that we now use this term in conversation, and that people who aren't, skilled in meteorology know what an atmospheric river is. Is that safe to say?
Well, it's hard to take credit for something that big, but I did restart the topic after it had sort of lost traction, and have built different programs and teams, and it's where it is today because a lot of people have been working hard on this. And I do think my initiative early on and perseverance through some headwinds has really helped it become more familiar today.
So you were like the atmospheric rivers PR person, basically. You brought it to the forefront, and now everybody knows what it is.
I was a stubborn scientist. Who said, no, this is a thing. The reviewers who didn't like it, I would make a case for it and get through the review process with the papers and ultimately proposals. And now we see really a whole community of people globally working on this topic. And it's really exciting to see how science can progress like that, and enable people to have careers that, focus on this and are making a difference in the world.
It is cool to have a meteorology term that has progressed so much in my adult life, because every other term has been around forever. Every other concept, at least, my level of expertise, has been around for a long time. I grew up knowing what hurricanes were, and I grew up knowing what, a tornado was, but I didn't know what an atmospheric river was. So it's cool to kind of be a part of this time period when this was happening.
I agree with you 100%. And it was a really important moment a few years ago where the U.S. National Climate Assessment, I think it's called, the fourth one. Previous ones had sections on extreme storms, but this new one added ARs to the list. In other words, it originally had, basically big thunderstorms, hurricanes, and winter storms. And by the time, that version of the climate assessment came out, atmospheric rivers had been literally added to the same page as those, traditionally well understood and respected topics. And that has been illustrative of how the topic has progressed. And at some point, I got a call from the editor of the Glossary of Meteorology saying we could really use a definition for this. So I organized a team of experts, and we had a town hall at AMS annual meeting, a town hall at AGU. We had, probably over 150 people attend those and have open discussion on it. It was a little bit of a controversial thing at the time. What is an AR? People had different opinions. Is it a thing? And out of that experience, we converged on an actual formal definition, which since then has been published, is now available in the glossary. And I've seen heard it gets a lot of attention.
Okay. So just so I can kind of get a feel for the timeline here, when did you start the Center for Western Weather Extremes?
2013, I left NOAA to join the university and start the center. It took about a year before I was in a position. I hired my first full-time person in 2014.
All right. So then from there, you're getting a better feel for atmospheric rivers and how to communicate them. And along at some point comes the scale, the categories. When did that happen, and how did that whole process work?
That's a really interesting story, actually, because it was a very singular moment I'll share in just a sec. But it was brewing for some years ahead. And for a couple of years, I had on my whiteboard a list of what are the characteristics of a particular storm and its environment it's hitting that will make an AR very impactful versus not. And I had 10 parameters on there. Way too complicated. And I was sitting at the AGU meeting in San Francisco, probably 2018, 2017 maybe. And I saw this big AR coming in our new forecast tools and diagnostic methods. And it was going to hit San Francisco on the very day I was giving like a keynote talk on ARs. We had a session in AGU. And I was sitting at this breakfast restaurant called the Sears Cafe. And the TV was on with the news, the weather broadcast. And there was the classic 5-day outlook, which had the high temperature, super boring, right? In the winter there, it's like either 55 or 58 or 60. Low temperatures, like maybe 45 to 50. But the first day was a nice, happy looking sun. The second day was like a pretty happy looking little cloud and sun. And then the third day was sort of a little bit more stormy, but, a cloud with some rain. The fourth day was a darker, threatening cloud with bigger raindrops. It didn't even come close to conveying the potential impacts of the storm that we could already see was coming. So it was at that very moment I decided, okay, ditch the 10 things and boil it down to the duration of the AR and the intensity of it over a point. And for each point, we could then classify it in some fashion. And we went forward and invented that together. I formed a team. 8 of us total, including a couple forecasters from Weather Service, including hydrologist, climate, a TV broadcast meteorologist, and I led the program or the development of it, and we published it in 2019.
So I'm curious because the Hurricane Center, has kind of caught some slack over the years about the Saffir-Simpson wind scale. I'm curious, did that play a role in what you decided there when you were coming up with this scale? Were you like, all right, they only took into account wind. It's not good enough, so let's do something better?
It's a good guess, but it's not exactly what happened. In fact, I don't think that influenced my thinking whatsoever.
Oh.
Because I had published a paper in 2013 that had shown with 91 different ARs, where we measured every hour the condition, the AR strength and all that. We could tell when it started, which hour, when it ended. We'd calculate the total water vapor transport in it and add that up. So let's say you had 24 hours of AR conditions at this site called Bodega Bay, north of San Francisco, where we had a wind profiling radar and GPS met receiver, so we get water vapor aloft. And we had a rain gauge in the mountains downstream or downwind, like 10 miles or so. And when you add up the total upslope component of the water vapor flux over those 24 hours, and correlated it against the storm total rainfall, it explains 75% of the variance in storm total rainfall. No agiostrophy, no worry about vertical motions, just raw water vapor flux straight into the mountain in an AR. The fact it's an AR comes along with what's called neutral static stability, which means that you push the air up a little bit, it's going to keep going. So that's one of the embedded characteristics of the AR. And ARs are in the lower part of the atmosphere, the lowest 10,000 feet roughly, and they have very strong low-level winds, sometimes hurricane force at 1,000 feet above the ground, and then lots of water vapor. So you combine all those three characteristics, and they are big rainmakers. So that study in 2013 really showed us that it's this combination of how strong the AR is and how long it lasts. And I wasn't going to create a scale that's a time integral, even though that's the physics of it. So we simplified it down to, as the AR is going overhead or predicted to go overhead, what's the maximum vapor transport? We call it integrated vapor transport, or IVT. And then how long in hours is the AR going to last? So the scale is based on those two parameters only. Compared to the hurricane categories, which are based only on wind, and don't factor in the duration of that hurricane over a given location, it makes it harder for that scale to be as representative of risk of flooding, because the stalling of a hurricane or tropical storm is really a central, consideration or factor in determining like what happened in Hurricane Harvey or Hurricane Florence. It's the stalling. So we really, from basic science, came up with what the two parameters needed to be.
So does that mean that it doesn't change over time? Like you assign it a category and it stays that way?
Yes. When an AR is predicted over a given location, let's say San Francisco, we identify the start time of it when the IVT goes over 250 units and the end time when it drops back below 250. Then we look for what the maximum IVT is during that period of time. Maybe it's 800 units. That would make it a strong AR from the intensity standpoint. And if the duration of the AR is 24 to 48 hours, that would make it an AR3. If it lasts more than 48 hours, we promote it to AR4. If it goes through faster than 24 hours, we demote it to AR2. That's how we factor in the duration. And that's the forecast of it for that location. Then once it starts and ends, we see what it actually was. So that becomes, the historical categorization versus the predicted. It's not like the storm changes its ranking. It's the forecast might change of what it's ranked, and we adjust our maps and all that accordingly. But that's how it works.
It sounds more similar. I always want to compare it to hurricane forecasting, but it sounds more similar to like solar storms and the way that solar storms are forecasted and then going back and saying, actually, it was a G4. So, okay, so let's say that's the case for San Francisco. What do you tell like Portland that that it's still this level, but for them, it's different impacts?
So, for example, the storm that is hitting right now is stalled. It's just north of San Francisco. And oh my gosh, 100 miles between that site that's had over a foot of rain in the last day or so to San Francisco, that's like less than 100 miles. San Francisco's hardly had an inch. So there's a really hard, sharp southern edge to this event. And we see that sometimes with the stalling ARs. So it's sort of easy to picture it as a fire hose, and it's stuck, aimed at that one area. It started with this bomb cyclone that happened recently, occurred off the Oregon-Washington coast. At some point, the AR ranking forecast, AR scale forecast, went from showing potentially AR3 conditions, say in the Washington coast, to, in the end, I think it was much weaker up there. It didn't last as long and wasn't as strong. It ended up targeting farther south. So if you look at our map on our website, you can see that the AR ranking has been a 4 now, basically from San Francisco to the Oregon border, and then weaker as you go farther north.
Are you ever going to start naming them?
That's come up many times, but there are too many ARs each year. So, for example, Southern California might get half a dozen, but that's pretty far out of the normal AR storm track. Central California might get a dozen per year. Northern California, maybe a dozen and a half. If you add up the entire West Coast, there might be 50 of them in 1 year. They don't hit the whole West Coast, right? They hit wherever they're hitting. So it's a little bit, I think, logistically not, feasible to put names, and it would get super confusing.
What is the season?
Well, it usually starts in Alaska in the September, October timeframe. And by the way, there was just yesterday a legislative bill introduced by Senators Padilla from California, a Democrat, and Senator Murkowski, a Republican from Alaska, to focus on atmospheric river forecasting. And it's a major bit of legislation. And the press release that includes a quote from Senator Murkowski highlights the incredible impact ARs have in communities in Southeast Alaska, including, sadly, a number of fatalities recently. So that season starts in the September-October timeframe, or is largely September-October into November. To get into Washington State and Oregon, it's usually November, sometimes October. November is usually sort of a peak, and November, December. Then it lets up sometimes in January, February, although there are some big ones in January and in the Northwest. Northern California usually kicks in December, sometimes in November, like we're seeing this year. And SoCal, it's usually more in the January, February, or even March timeframe that's active for ARs. And then it tends to settle down by April or May.
Does El Nino or La Nina impact atmospheric rivers?
Interestingly, that's been a very common perception, but it's remarkable that we really haven't been able to show that. There's been a recent paper that's identified some connection, but I haven't had a chance to read it yet, so I have to look at that more carefully. But our studies more recently have shown that, in fact, ARs are the disruptor for Southern California of what one might normally expect from El Nino or La Nina. In the last 20 years, there have been, say, 4 El Ninos and 4 La Ninas, the La Ninas have been unusually wet in Southern California, which is usually, when we expect dry. And the El Ninos have been sort of ho-hum or even a bit on the dry side. And when you look back at the count of ARs that hit Southern California, that basically explains the difference.
You mentioned an update to the ranking system. Can you tell me what the ranking system logistically looks like right now and what that update is?
So there's a little matrix, a colorful matrix from green to red for AR, or blue to green to anything else. Colorful for AR 1 to 5. But the minimum value of the vapor transport of IVT is 250. For the polar regions, there's just not that much water vapor to move around because the air is so cold. But in the polar regions, despite there not being as much water vapor relative to our 250 unit IVT threshold, the ARs, the weaker events than that, are major players in the climate for the Antarctic. And that we've come to realize that we can simply extend that matrix figure and the parameters it represents downward to lower thresholds of IVT. So now we have 3 rankings of polar ARs. Polar AR1 is 100 to 150 units. Polar AR2 is 150 to 200. Polar AR3 is 200 to 250. And then above 250, it becomes AR1. We use the same duration criteria of shorter than 24 hours or longer than 48 to determine whether they're promoted or demoted. And we've now literally done the calculations of the frequency, the contribution to precipitation annually and all that. And we just published it in the journal Cryosphere, and it's in print as of yesterday.
Okay, I am curious about kind of authority to do different things with ARs, like ranking them, because, you're not the National Hurricane Center, part of this NOAA entity, you're part of a university, right? So how do you think there's a future where there is like the National Atmospheric River Center, like you transition into that, or how does that all work with this government entity?
Yeah, the organizational shifting thing, I'm not sure how to handle that. But the fact is that this topic, the innovation has been occurring largely in our university center and university colleagues. We have partners in the National Weather Service and in NOAA more broadly, particularly in the Office of Marine and Aviation Operations. They help fly the AR recon missions each winter. And in the U.S. Air Force Weather Reconnaissance Program squadron, we use their aircraft and their great teams as well. So it's really emerged organically because of the innovative nature of being at a university. And there's a demand in the West, in particular, for knowing whether the incoming storm is going to be a big one or not. And in the past, the way of articulating that has been way too complicated for people to understand. So this boils it down to a very simple ranking system that is intuitively, reasonable, and it has become popular and useful from everywhere from, members of the public. When they hear who I am, they're like, "Oh, I love your scale," to, media sharing it, to decision makers at the highest levels monitoring this on a regular basis, whether they're resource managers or elected officials. And it gives them really a heads up, a situational awareness improvement, or an improvement of their situational awareness about, well, is this going to be one of those storms we really need to be paying attention to? And if it is, then the point of the scale is, okay, we got their attention. Now they're going to look at their standard or their preferred, weather detail forecast provider, whether it's the National Weather Service or others. They can then, and that's how the weather business is now, right? There's a lot of private sector entities doing forecasting. Our university is sort of like one of those. We have a lot of forecast tools. People are using them a ton. So that's how it's emerged organically in the face of an absence of something. We've invented something that's shown value.
I want to go back to the reconnaissance thing because I'm curious about when that started. It seems really convenient that these are happening in the hurricane off season where this fleet of aircraft can just come over to the West Coast and start flying in. So how did that program start with both NOAA and the Air Force? And then I also want to find out what it's like to actually fly into an atmospheric river. Sounds rough.
It's an interesting story, once again, of grassroots, science-based, development. And the logical thing, these aircraft are not so busy in the winter. And so I I started my first sort of look at actually deploying specifically for what we now call AR Recon was part of another program I co-led the development of called Cal Water. And that included funding from several agencies, and it was to study aerosol impacts on precipitation and AR dynamics. And we flew some aircraft offshore, including the NOAA G4. And in one of those last campaigns, we did 2 winters with aircraft. The main purpose of the G4, we were flying straight across the AR to do drop-ons so I could measure the flux of water vapor. Remember I mentioned the 25 Mississippis? It was those 2 winters with the G4. We sampled like 17 storms, and we were able to calculate what the average AR water vapor flux is with that. But at the same time that we were doing that scientific study, we tried to get those drop-ons transmitted in real time for possible assimilation by the global models. We're collecting them anyways for the research. Let's see if they're useful operationally. We didn't have all the mechanics set up to do that so well at the time, but it really served as an example. And those years were 2014 and 2015. 2016 was then another predicted big El Nino year. By the way, one that turned out to be a dud for Southern California. And in late in the fall of 2016, I had an opportunity to make a pitch for using 2 Air Force C-130s for 2 weeks in February to try out the AR Recon concept. And by then we'd had done a little bit of planning about what it would look like and how it would work. And that was when we had our first flights of AR Recon. And I teamed up with Vijay Talapragada, the National Weather Service leader of the GFS model and well-regarded scientist and forecaster. And we have built AR Recon up. From that winter, we flew 3 storms with 2 aircraft in each storm with many drop-ons. We've got the data into the models. Then we flew again in 2018. Interesting sidebar, why not 2017? Because as a scientist and resource manager, I wanted to take that winter to study the data from 2016. Guess what happened in 2017?
What?
The wettest year on record in Northern California. The Oroville Dam spillway incident that caused 183,000 evacuations. And never again will I be so conservative. But anyhow, we got back to it in 2018, and we did 6 storms, once again with 2 C-130s. And then the next year, 2019, we did that again. And I think in 2019, we might have gotten the G4 for the first time. And I, paid for some of this with research funding to do the pilot study stuff, and worked closely with VJ at NWS. And we did data denial analysis to see when we added these data, did they help? And they were showing good evidence of helping. So by 2020, AR Recon became the core element of what's called the National Winter Season Operations Plan for the U.S. weather reconnaissance capabilities. And from that day forward, it has been the top priority of the Winter Season Operations Plan as part of the formal, designation of priorities that's done by the national, community of people involved in weather reconnaissance, including National Weather Service and Air Force and all that. And it's been now this last winter, we flew 40 different days, including a 2-week period where we got to operate out of Guam for the first time. And the goal is to have a full-fledged AR Recon capability from the 1st of November through the end of March, flying on the order of 60 days each winter. And this is based on what we've actually determined is the need from trying to do this. Like, we've called for flights this week, but the aircrafts haven't been available because of still some active stuff in the hurricanes and also, capacity challenges in general. But those aircraft really could have been useful in November, but it overlaps hurricane season by a month. So we got to work all that out. There's solutions there in the end. People will be reasonable.
Have you gone on any of the flights? Do you ever go on the flights?
Yeah, I go on a 1 or 2 flights each year, and often I'll go with an executive or a media person who hasn't done that before. And often their reaction is, well, it doesn't look very exciting out there. There's no big thunderstorms. It's not like the eye of a hurricane. And I finally realized, because often as the AR doesn't look like much from the sky. It's just a bunch of clouds at low levels, even super clear above the mid-troposphere. And then sometimes there's more action you can see as it gets into some upward motion and more clouds at mid-levels and upper levels. But I realized sitting in a cockpit with a reporter 2 years ago, you know why? They basically have been hidden in plain sight. They don't look like much, but when you drop the sonde through it, it might be pumping away at like 25 Mississippi rivers worth of water vapor transport. So that's partly why the topic hadn't really matured earlier, I don't think, is because it literally doesn't look like much.
So are you flying above the atmospheric river?
We're typically up at 30 to 45,000 feet, and it's often above the cirrus clouds even, and it's really beautiful. Quite, you can even see at the 45,000 foot level, you can see the curvature of the earth a little bit, and then you can look down and see through the gaps in the clouds. You can see the ocean. It's really spectacular. But these flights are exciting to go on, and they actually can have more clearer turbulence or more turbulence than often the G4 flights, the crews had told us, see in the hurricane situations. So although it's not necessarily cloudy up there, there's a lot going on dynamically, including conditions that can create clear turbulence.
Okay, so you mentioned drop sondes. Is there anything else that you're dropping down into these? Are there drones going into them at all?
There's a couple things we're doing. One is a development project for several years now, led by a professor at Scripps named Jennifer Haas, and it's called airborne radio occultation. You've probably heard of radio occultation from GPS satellites. When you have a GPS receiver on the ground and the satellite sets on the horizon, the beam of light from a signal from the GPS satellite at the receiver, you can then get that's a bent as it goes through the atmosphere, and the bending is related to the temperature and moisture along the ray path from the satellite to the ground. Well, Jennifer put onto the aircraft a GPS receiver and figured out how to track all that stuff, and it's pretty amazing. So the drop sondes are looking down straight from the airplane, right? The radio occultation work is looking out to the sides, out to maybe 100 or 200 kilometers, even more, but it's a very different type of measurement. And the two combined, I think, is going to be a real winner long term. In addition, the ocean, of course, is super important for the weather. And in particular, ARs get their moisture, essentially their water vapor, from the ocean surface. So ocean conditions are really important to monitor. And there's a global drifting buoy program that deploys, there's maybe 1,000 of them around the world at one time. And one of the major institutions that deploys them for NOAA is Scripps, and there's a colleague of mine there named Luca Centurioni, who we have coordinated with. And only some of those buoys go out with sea level pressure measurements on them. The buoys last a year or two, and the sea level pressure measurement sensor can be added at fairly low cost. So I've been investing as AR Recon lead in putting 50 to 100 of those out each winter in the Pacific with this colleague, Luca Centurioni. And it's leveraging the very important NOAA program, Global Drifter Program. And those data are really important as well. So we now we're responsible for about 11% of the global number of sea level pressure enabled buoys that are drifting around, in the ocean, in the oceans. And we're trying to expand that. These data have impact on the forecast skill through assimilation as well. And then the last thing I'll add, well, there's two more real quick. One is going into the subsurface, below the surface of the ocean. The mixed layer of the ocean is important. And we have the good fortune to be able to deploy some sensors that go up and down in the ocean. They're ocean profilers. And they go down as far as 2 kilometers and then come back up. And we're also leveraging the Argo buoys, which go up and down. When they're up close to the surface, we can take advantage of that to know what the ocean's doing. And then the final thing I'll mention is a private sector entity called Windborne Technologies, which has drifting balloons that are now able to descend and reascend like a dozen times over several days as it drifts along with the winds at high altitude. And they can sort of steer it because they can adjust the altitude range. And those data are looking really helpful. they are likely to be able to, they're very complementary to the aircraft. Think of the aircraft as, think of the drifting balloons as providing like a large aerial pattern observation. And the AR recon aircraft flights are like the surgical incision right through the AR, precisely where we know the biggest uncertainty is coming, error sources are for forecasting. Those two combined, plus the ocean measurements, plus the sea level pressure on the ocean, and in the future, this airborne radio occultation is going to be really effective in improving predictions in the Northern Hemisphere.
Wow, cool. What about sail drone? Do they go into them at all?
We haven't had a chance to work with sail drone. I think there'd be some very interesting things that they could do that complement this stuff. And that's, I should mention, part of what AR Recon is an umbrella effort that isn't just about the aircraft. It's about these various sensors really trying to fill in situ or, in place measurement capabilities in the atmosphere, which really complement the satellite data. Interesting side point, just published this August is a paper we've done. Minghua Zhang is the lead author, and she did a data assimilation study of the dropsondes. And when the satellite data, there's microwave data, can see into clouds and precipitation, and that data can be assimilated. But a lot of that data, the model kicks out because it has too much uncertainty, partly because it's in clouds and precipitation. The measurement just has a lot of uncertainty. And when you have a dropsonde nearby, some of that satellite data, the dropsonde provides an anchor for the data assimilation system in the model to say, oh, that's what's really there for sure. Now we know what satellite data around it is accurate enough that they can assimilate it. So by adding the dropsonde data, it's allowing 5 to 10% more of the satellite data actually to be assimilated by the model without being kicked out. So it's really a win-win situation to have these additional in situ measurements in the ARs, right where clouds block a lot of the satellite type measurements and where the radiance or microwave radiance measurements have their largest errors. So the combination is really potent.
I'm curious about outlooks, and I know we're into the season already, but do you have any way of kind of looking at the season as a whole and making a guess as to active or less active?
Everybody wants to know that. And, the skill in doing that is pretty poor. The ocean conditions are really important there. And it's sort of been on verge of La Nina conditions this year, which would tend towards the Pacific Northwest being wetter than normal, and Southern California being drier. But like I said, these ARs are sort of the disruptor of that correlation, and we don't really have a good way to predict the months ahead, the occurrence of ARs. We're working on what's called subseasonal forecasting, specific to ARs in week 2, week 3, week 4, week 5, and week 6. There's not a lot of skill out there at week 6, but the Mann-Julian oscillation offers some potential there. And then also the QBO comes into play with that. It modulates the relationship. And at weeks 2 and 3, we're seeing some emerging skill using some new diagnostic methods that we've developed that focus on the AR occurrence.
Is there anything else, Marty, that you want to add about atmospheric rivers? This has been really, really interesting. I feel like I could ask you questions all day.
Atmospheric rivers are a really important thing for water in many parts of the world, whether it's to help alleviate drought or to cause flooding. They're often the game-changing phenomena. There's also a lot of opportunity for early career people to get into this field and make a contribution, genuinely, as scientists or engineers or forecasters. And we're seeing that happen in front of our eyes. And it's a wonderful thing. And it builds on the incredible foundation in meteorology around the dynamics of mid-latitude storms, whether it's cyclogenesis or bomb cyclones or frontal behavior or other things. It's now another way to look at the weather conditions that gives us additional insight into how it works and what might be coming.
Yeah, the recent headlines were, atmospheric river meets bomb cyclone, impacts destructive across the Pacific Northwest. So is that common for an atmospheric river to interact with a bomb cyclone and have this kind of impact?
Quite interesting question. When an extratropical cyclone is just beginning, we call it cyclogenesis, right? The genesis of a cyclone. That is a specific location that's surrounded by various weather conditions. We've done a study of 3,000 cyclogenesis events where we asked, was there an antecedent atmospheric river near that cyclogenesis location? And we found that about a third of cyclogenesis events have an AR already present nearby. In those cases, the cyclogenesis deepens 50% faster than without an antecedent AR. And 60% of all bomb cyclones have an antecedent AR present. And when that AR is super strong, like an AR5, it supercharges the cyclogenesis and really contributes to it becoming a bomb cyclone. And then the bomb cyclone can modulate the airflow patterns and the AR and boost it up or move it around. And then there might even be a remnant AR left behind after the bomb cyclone moves away. And another cyclone can develop that taps into that remnants of an AR. It might even still be an AR.
So the AR is the fuel that is creating the bombogenesis. I'm almost picturing like the satellite with like the, the cyclone just eating up the atmospheric river. Awesome. Marty, thank you so much for your time. I've learned so much today, and I hope this helps other people better understand atmospheric rivers too.
Thank you for your interest and really excellent questions, and look forward to seeing your work.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes publish every Tuesday. If you know someone that's interested in learning more about atmospheric rivers, please share this episode with them. We'd also love you to rate and review us on Apple Podcasts and Spotify. You can let me know what you think of the show. You can also give me ideas for future episodes. Special thanks to Dr. Marty Ralph for all of his time and expertise today. Also, thank you to Sinclair Broadcast Group and the National Weather Desk for their ongoing support. And as always, thank you to my associate producer, Brian Petrus, for his help on this episode. I'm meteorologist Emily Gracie. Make it a great day.